Welcome everyone to this week's Quantum Theories of Fields, Matter and String seminar series. We are very happy to host Fiona Burnell from University of Minnesota. She will talk about her recent work on LSM theorems to apply to higher multiple moments. Fiona, thanks a lot for accepting our invitation. We are very happy to host you. You can take it away.
Yeah, sounds good. Yeah, so the title that I gave in my email was a little bit more exciting, but this is a more technical title. But really, this is a talk about, the basic question, which is actually super important in understanding materials, which is, when can I lay out some very basic conditions under which I can guarantee you that some material does not have a kind of a boring ground state, okay? So that's really the theme of what we're going to talk about. And so this theme starts with a really basic question. So in a lot of materials, right, we're talking about some kind of crystal, and a lot of the time to understand the properties of a crystal, one of the main things that we're thinking about is, kind of assume that the atomic nuclei are basically fixed in space. And we're talking about how the electrons are moving around, and what they're doing inside the crystal. Okay. And, when I do this, so I typically have a crystal has translation invariance, not continuous translation invariance, but if I move by one, kind of crystal lattice spacing, things look the same. Okay. And typically when we have these crystalline systems, right, you have a scenario where you have, the electrons have some energies that they're allowed to occupy, where the energy of an individual electron sort of depends on its momentum, right? So here's a sort of a sketch of what an energy momentum relation for an electron living in a crystal can have, okay? And so this is called band theory. And this is like a nice picture that we can have for electrons in materials in the scenario that the interactions between the electrons are not very important, okay? And again, the fact that the energy of the individual electron is a function of momentum, this is, of course, requires the translation invariance of the crystal. Okay. And so electrons in crystals fill these energy bands, okay? And because translation is not continuous, actually, and this is something, if you haven't seen this is something that you should take your favorite computer program and plot on a lattice, the function some sum over k's of alpha k e to the I k a, okay. And the other function with the same alphas, okay. And you can take your k's and so this is some function. Well, let me write it as e to the I kx, okay? But, I'm going to take k plus 2 pi over a times x, okay? And if I plot this on a lattice where x is multiples of a, then what you will see is that these two are the same thing, okay? So this, this momentum is sort of periodic. It goes from minus pi over a, okay, to pi over a. This is my sketch of an electron in a crystal. And one thing you notice, right away is that it matters how many, okay, and you can count the number of states in here, okay? Oh my gosh. And if I have, I have a, there's some details of the model. Basically, you can count the number of states in here, okay? And you can imagine sort of two scenarios. So one thing is, if every state in here is occupied, and in a system with spin, this would be like 2 electrons per atom in my chain, okay? Then, this system, there's sort of nobody, it has a Fermi surface, there's nobody near the Fermi surface, and this system can indeed look very boring, okay? On the other hand, if the system is at half filling, which for spinful electrons, again, would be 1 electron per atom, in the crystal, you notice that in this non-interacting case, okay, now here's the Fermi surface, and I have electrons that are near the Fermi surface. And so this now is a metal, okay? So if I have filled all of the states in my band, I have 2 electrons per atom, I have an insulator, okay? It is kind of boring at low energies. I poke it with fields and nothing happens. On the other hand, just by changing the filling, I change from an insulator to a metal, okay? And you can then ask, okay, so this is like a very simple observation that you would see the first time you take a condensed matter course, and you can ask, is this just a property of the non-interacting system, or is there something more fundamental going on that I could use to draw conclusions about materials, maybe even in the presence of strong interactions where I can't, solve the problem analytically so well. And so you might ask, well, let's look at the opposite limit. To start to understand this, let's look at the opposite limit, okay? And the opposite limit is where the interactions are very strong, so that my system only wants 1 electron per unit cell. Sorry, one electron on each atom, okay? 1 electron on each atom. And you might say, well, 1 electron on each atom, that's, if I only thought about the charge of the electrons, that's a unique state, of course. But these electrons have spin, right? So as soon as I have only 1 electron on each atom, now basically what I have is I have to ask, well, is the electron spin, doing something interesting, right? So maybe it doesn't, it's an insulator, it doesn't conduct electricity, but maybe it has some interesting magnetic properties, okay? And so you can ask the question, well, does it matter if I have a single spin a half per unit cell versus, maybe 2 spin a halves per unit cell, or fully filled, which is the analog of our fully filled band versus our half filled band. And right away, when you look at these pictures, you can sort of see that it does, okay? So this is a cartoon of, if I have an even number of spin a halves per unit cell, okay, I could sort of draw the 2 sites in the unit cell as the, let me get the pointer, right, as the top and the bottom of this chain. And then I could sort of ask, well, are these guys talking to each other? How much are they talking to each other versus how much are they talking to their neighbors? Okay. And so if I look at this situation with 2 sites per unit cell, whether I draw it like this or I draw it like this, one thing you can certainly do is you can imagine a limit where the 2 spins on each site are very strongly coupled with each other and not very strongly coupled with neighboring sites, okay? And one thing that I can do if I strongly couple spins to each other is I can take those 2 spins and I can put them in a spin singlet state, right? So net spin 0. And so in this way, my spin a half chain could turn through interactions to a spin 0 chain, right? And a spin 0 chain is a pretty boring thing, right? It's just, spin 0 on each site. This is a very boring kind of ground state. Okay. So that's something that I could do. On the other hand, you can sort of convince yourself, so now we're looking at this case where on each site, on each unit cell of my lattice, I have a single spin a half, okay? And you can ask, well, what could I do to this system, to kind of get to what could I tell the spins to do to have them pick some kind of ground state, right? And there's some familiar examples. One thing I could do is I could tell them all to line up, as is the case in a ferromagnet, right? But this, of course, breaks the spin rotation symmetry. Another thing I could do is I could have them, want to anti-align with their neighbors. So this gives us what we call an anti-ferromagnet. But this breaks translation symmetry, okay? And another thing I could do is I could have them, again, do this thing where they pair with they pick one neighbor and they pair with it and they form a singlet, okay? But now, so before these 2 were was a single site, a single unit cell in my lattice, right? So this didn't break translation. Now it breaks translation symmetry, okay? And so all of the kind of obvious choices that you might think of to have these spins pick some specific ground states, break symmetries, or the other choice, for those of you who've heard, the term sort of Luttinger liquid, this is, something that happens a lot in one dimension. The other choice is they could be gapless. Okay, so maybe the charge is gapped, it's insulating, but you still have some kind of transport of spin. Okay. So clear
Can
so
I ask
far?
something?
Yeah.
So by a boring ground state, was meant is essentially a ground state that realizes symmetry when nearby, so there's no symmetry breaking, and it's a unique ground state. So that's your
That's
definition
right.
of a boring ground state.
Yeah, a unique ground state that is separated from the rest of the spectrum by a gap, and yeah, preserves all symmetries.
Okay.
Yeah, yeah.
And all the rest are more exciting, like not boring in that sense. Okay.
Yeah, yeah. I mean, I think whether you think about something like a ferromagnet as exciting or not is a bit of a matter of opinion, but there's some sense in which you should think about a ferromagnet as kind of not so boring. And the reason is if you take in the right, so when you learn about like the Higgs mechanism or spontaneous symmetry breaking, you talk about the thermodynamic limit and you talk about how the system sort of selects a vacuum. Okay. Now, if I think about and so for continuous symmetries, if you spontaneously break the symmetry, you have Goldstone bosons. So that's actually a gapless state. So that sort of again falls under the criterion of it's not really boring because it has these Goldstone bosons. For discrete symmetry, if you think about like an Ising model where the spins only have two choices, they either point up or point down. If you look at a finite-sized, Ising system, you don't have Goldstones. It's a discrete symmetry. But on a finite-sized system, the true ground state never breaks the symmetry. Okay, the true ground state is a quantum superposition of everybody being up and everybody being down. And this is actually it's an entangled state. It's not something that you can create from a product state using some kind of local, unitary evolution. So, yeah. Sorry, a bit of a
so what about SPT phases then? I mean,
good. Yeah, so SPT phases are, I think we would SPT phases are a particular version of not boring where so another definition of boring is that I can take my Hamiltonian, change it adiabatically without going through a phase transition, and deform it into something whose ground state is really just a completely unentangled product state. Okay, and so when we talk about SPT phases, the criterion, the kind of definition of an SPT phase is that you can't adiabatically continue the Hamiltonian to something that has this like symmetric product ground state unless you break the symmetry. So there you kind of have this you have to add this additional criterion, which is that it's a distinct phase of matter, which has an interesting ground state only if you're really talking about the situation where you preserve the symmetry. But today's talk is also relying a bit on symmetry, so it's kind of a similar situation. Yeah, good. Okay. So, the basic question here. So what we've seen, right, is just in kind of thinking about these familiar examples, the Mott insulator limit, the band insulator limit, okay, what we've seen is that it kind of looks like if I have a single electron in each, unit cell of the lattice, right, I'm at this half filling, that there's some obstruction to making a sort of trivial gapped ground state without breaking, either the, spin rotation symmetry or translation symmetry. And it turns out that this is, something, so when people say the Lieb-Schultz-Mattis theorem, this is basically this result. They proved it for, spin systems, okay? But the answer is, this is not just a coincidence, a feature of the two limits we were thinking about, but this is a fundamental fact that with an odd number of electrons per unit cell, you can't have a system that has a totally, boring ground state, right? Gap symmetric, non-degenerate. And by the way, so why is it useful to know this? Well, It's useful to know this, among other things, if you're interested in finding materials that host more exotic phases of matter. So, one of the things that condensed matter physicists have been interested in doing for a long time, dating way back to the 1970s when Phil Anderson first proposed the idea, was find a material that's definitively a quantum spin liquid. And this Lieb-Schultz-Mattis theorem is really useful because it tells you that, it's not helpful for asking, well, when are my magnetic moments going to order and break the symmetry? But it is useful for telling you that, you should be looking at systems that have an odd number of electrons per unit cell, because they're at least, they're not going to be some trivial band insulator. Okay. So it's a useful guiding principle in thinking about what certain materials might do. Okay. So what I wanted to do today is I'm not going to give you the Lieb-Schultz-Mattis version of the argument, but I'm going to review a different version of the argument due to Masaki Oshikawa, which explains where this obstruction comes from using a very simple thought experiment involving gauge fields. So I'm going to go over that argument, and then I'm going to talk about what happens when we extend this, this idea from systems that conserve charge or spin to systems that actually conserve, dipole moment in one dimension. And you could extend it to higher multiple moments if you wanted. Okay, good. So why is it that, so now I've been talking about spinful electron systems, and I should say that in the rest of the talk, I'm actually going to talk about only electric charge. So you can think of this as I'm talking about fermions, but I'm imagining my fermions have no spin, okay? Or maybe I'm talking about bosons, but I have, a system which only has one symmetry. I'm going to refer to it as a charge conservation symmetry, okay? Plus translation symmetry, so I guess two symmetries. This system is going to live on a 1D lattice with periodic boundary conditions, so a 1D ring. And because the system has this, U1 symmetry, what does that mean? It means that this total charge, okay, which is the sum of the number of particles on each site. So Nj is just this number operator. We would usually write it like C dagger J, CJ fermions. Maybe these are bosons, okay? This operator, this total number operator is conserved, okay? So now there's a tight relationship between the conservation of this number operator and the symmetry, okay? And so the global symmetry basically says, that's kind of usual definition of the global symmetry, a global U1 symmetry, if you've sort of studied it in quantum field theory or something. Here's where I'm going to have trouble with my toolbar. The definition of it is basically that I take the fermion creation operator, right, and I rotate it by a phase. And what is the operator that carries out this phase rotation? Well, that operator is e to the I alpha q, where q is this, oh dear, q is this number operator here, okay? So that's what we're talking about. This is the global phase rotation. Okay. So now I can ask, okay, so we are going to get to fillings, but there's sort of some basic games you might play with your particle on a ring. And one of the things that you might do to your particles on a ring, okay, is you might insert some background magnetic flux through the center of the ring, okay? And let me just remind you, so, and maybe if people have not ever heard of a Aharonov-Bohm phase, we should stop and go over that. So maybe I should just ask that to you guys. Is everyone happy with the Aharonov-Bohm phase? Okay, perfect. So what does this look like? What happens, what does my particle on a ring see when I insert this flux through the middle of the ring? Well, basically what happens is that, how does the charge feel the flux, right? So I can have flux through the middle. As you know, I could poke a solenoid through the middle of the ring. So there's no magnetic field, there's no electric, field, except when the flux is changing, okay, acting on the particle, right? So once my flux is there, it's just sitting there. You're like, how does the particle feel the flux? And the answer is the particle feels the existence of the flux through the Saharonov-Bohm phase. So if the particle goes all the way around, right, and here I've set the, charge, I'm measuring charge in units of E, so my charges are like integers. So I've left out the E's, right? But now, if I took one particle and I brought it all the way around the system, and this particle has integer charge, right, the wave function is going to get multiplied by this phase. Okay. So the particles feel the magnetic flux unless, of course, the magnetic flux is a multiple of 2 pi. Because if the magnetic flux is a multiple of 2 pi, right, then, oops-a-daisy, then this phase factor is just 1, and no particle can tell that you had that flux of 2 pi through there, okay? So you can ask, what happens if I thread one flux quantum? And, physically, the system before and after the flux threading are the same. The no particle, the Aharonov-Bohm phase is trivial. Okay, physically, everything is the same. But there is basically what you're doing when you compare the system with flux 0 and the flux with flux 2 pi is you're now working in a different gauge. So you can, the kind of term that's often used for this is you've made a large gauge transformation, okay? So there's a flux, and that means that, an appropriate choice of gauge for flux of 2 pi is that I'm going to pick my gauge field to be constant, right? So no electric fields, no magnetic fields, and it's a constant of 2 pi a over L. And what that means actually is that, this winding of A as I go around the circle is going to be 2 pi. So these are like basically physically the same, but there's a nuance to that, which is that they're related by this large gauge transformation. And large just means that the winding of the gauge field changes. Okay. So Masaki's insight about this was that if you want to make a fair comparison of what happens when I insert my 2 pi flux through the system, okay, so we're gonna come along, we start with our system, we're gonna very slowly insert a flux of 2 pi, and we want to know what is that going to do. One of the things that he pointed out is that you should compare apples to apples. So to understand what this flux insertion does to my state, I should make a gauge transformation back so that I look at my system in the original gauge. Okay. Now, so, and I should just say, and maybe I'll actually write this. So, remember the global symmetry, right? The global symmetry was this e to the I alpha sum over j and j, right? This is the global symmetry. This commutes with the Hamiltonian, can't change the energy, blah, blah, blah. If I want to perform a gauge transformation, right? So a gauge transformation means that this coefficient, j here, is allowed to vary, from site to site. And I've chosen to put j here because this particular choice of j gives me this particular phase rotation, which corresponds to the large gauge transformation that changes the winding of A by 2 pi as we go around. Okay. So this is what we do. We do this large gauge transformation. And then we ask, okay, now I have performed a process. I have slowly inserted this 2 pi flux. And I'm looking at my system in the same gauge. What has happened to my system in that process? Okay. And so the first thing is that I can do this flux insertion in a completely translationally invariant way. So at no point in this process should I fail to conserve momentum, right? So the total momentum should be sort of conserved. But our large gauge transformation, interestingly, doesn't necessarily conserve the momentum of the state. So just to be clear, okay, so the oops, hang on. How we're going to look at this, oops, sorry, here we go. So how we're going to look at this is the following. So, you know, what am I using for my definition of momentum here? Here I'm using the eigenvalue of the translation operator, right? So if I translate by one site, this should be translation by A, I get e to the I p, p being the total momentum, times A, okay? And so this translation operator, you know, in terms of the ends, it just, you know, shifts j to j plus 1. And you can ask, you know, suppose that before I perform my gauge transformation, this, you know, this translation gives this number p naught, right? That's my initial many body momentum, okay? Now I'm going to apply this large gauge transformation. So to get to, you know, so this state psi prime is given by carrying out this large gauge transformation on my initial state psi, okay? And I can ask, what happens if I act with translation after doing that, okay? And what you find is that if you switch the order, if you pull the t operator to this side, right? So that basically means that you are translating you know, the nj's by one site, okay? That and then act on the state. So that's going to give you p naught. But in pulling the t past here, you get an extra phase factor, okay? And this extra phase factor, okay, I'm going to get rid of this. This extra phase factor is just this e to the 2 pi I, you know, times the charge filling. So the number of charges that you have on each side of your lattice. Okay.
Can I ask something?
Yes, go ahead.
So you should somehow be able to see this insertion of the flux as insertions of the symbol, right? And
insertions of okay, yep.
And based on what you just said, can we say that there is some mixed anomaly between the corresponding symmetry with the Wilson line and the translations because of the phase factor?
Okay, so that's a bit of a matter of opinion, and for the following reason. So if I, you know, and this is the typical perspective that a condensed matter physicist would take, if I view this Q, okay, as a number, right? It's fixed, it's conserved, I'm working, you know, at some fixed charge filling, then yes, absolutely, this looks exactly like an anomaly. I'm inserting a flux of the U1 symmetry, and I'm changing the momentum, in other words, the charge under translation. On the other hand, you know, if you sort of wanted to work in the whole Fock space, Q is actually, it's an operator, it's not just a number. And so if you take that perspective, you know, you would say, okay, it's more than just a phase, it's a whole different operator, and this is sort of a slightly different beast. It's a different kind of extension of the symmetry algebra to a larger group. So, you know, for example, Nadi Seiberg and Chu-Heng Shao and friends have, you know, a number of papers where they talk about, you know, these things for dipole symmetries, among others. And their perspective is Q is an operator, so you shouldn't think of this as an anomaly. But often in the condensed matter literature, you know, it is phrased as an anomaly. And that's just a matter of whether you want to live in a world where, you know, you're looking at a, you know, particular charge sector of the Hilbert space, or where you're really kind of looking at all of the possible charges that your model could have.
Okay, but when you said that when we look at it as an operator, there is some extension of the group. Isn't that just what an anomaly does? Like if it's a central extension, that should essentially be a Tufte anomaly, no?
Yeah, but I think here, so central extension, you know, really means that you obey the group multiplication rules, you know, like the, you know, kind of the operators have the same multiplication in terms of how they act on states, right? But they just differ by a phase. And so this is not, you know, if you are talking about, if you're acting on, you know, the Fock space. Okay, so you're including all of the states with different charges. This is not that, because it's really a different operator, right? So now you just have a different sort of group. You know, the whole symmetry group is different because it's not true that you still get the same group generator. It's just different by phase now. Now it's a different group.
So it's not like a symmetry extension, but it's a different group. Okay.
Yeah.
That's why it's not an anomaly.
Yeah. So, I mean, yeah, that's right. So, you know, like I said, if we're thinking about a fixed filling, I think it's totally fine to think about an anomaly as an anomaly. Otherwise, it's something a little bit, you know, different. Yeah.
Thanks.
Yeah, good. Perfect. So, yeah, so now we can ask the question, does this process of like adiabatically inserting the flux and then, you know, because remember, we always have to compare apples to apples, right? So the momentum is not gauge invariant. So if we want to talk about the momentum, we have to do this gauge transformation back to our initial configuration. And so when we do this, we can ask, has this process changed the total momentum, right? And what we've just seen is if the momentum before the flux insertion plus gauge transformation is P naught, then after this process, it's P naught plus 2 pi nu, where nu is this charge filling fraction, right? It's this Q times the lattice constant divided by Lx. And so what we see is that if the filling is an integer, right? So here we've gotten rid of the electron spin. So if I have like 1 electron per unit cell, 2 electrons per unit cell, okay, or charge 1, charge 2 per unit cell, then actually the momentum, because remember, momentum here is conserved only up to this, factors of 2 pi, again, because this is a crystal momentum, we don't have continuous translation. So if this is 2 pi times an integer, then P naught, then P and P naught are equivalent, okay? However, if this filling is not an integer, if it's fractional filling, right, then this process has changed the momentum of the many-body ground state, okay? Now, this tells you that basically the many-body ground state can't be boring, okay? And the reason for that is that if I insert this flux very slowly, right, and I have just a unique gapped ground state, okay, so yes, to insert the flux, there's going to be some electric field, but I can make that electric field very, very weak, right? So remember, in an insulator, you need to have a finite amount of electric field to do anything. So, charges are not going to move. And so basically in this flux insertion, a unique, gapped ground state is nothing's going to happen to it, okay? And in particular, it's not going to push it out of the ground state because there's this big gap and the electric fields are always really weak. So if you have a unique gapped ground state, then this process has to keep you in that state, okay? But if you're in the same state, you better have the same momentum, right? And so that's how you get a contradiction. So basically, if you're at integer filling, and again, we're just doing charge, no spin, then there's no obstruction here to having a unique gapped ground state. And, I think it's kind of obvious what that unique gapped ground state would be. It would be that I put, a single charge on each side of the lattice, right? And that is a product states, and it respects all of the symmetries. But if I am at fractional filling, then what we've learned is that, no, it's not just that you're not creative enough in writing down, gapped ground states, that you're not finding the right one. It really is that there is no unique symmetric gapped ground state. Okay. And so, like I said, the sort of moral is that, the naive feeling that you have that, look, if I have an integer charge per site, I can have this state, and that's a product state. It's very boring. But if I have a fractional charge, well, the boring states that I can write down are something like this, and they break translation symmetry, right? And they're not unique because I can translate it, and I would get a state of the same energy. Okay. This is, like I said, not just a lack of creativity on our part in thinking about states, but this is about what ground states our fractionally filled system could have. This is a fundamental obstruction. Okay. Are there questions about this? Otherwise, I'll talk a bit about the dipole case. Okay, excellent. Okay, so then, yeah, what I'll do in the next part of the talk is I'll say a little bit about how you can extend these ideas, beyond charge conservation, specifically to dipole conservation. And I should say that the gist of Masaki's argument, an ordinary sort of global symmetry with, whether this is conserved charge or conserved spin, you can generalize this argument. It's a very nice argument. But I want to talk a little bit about the case where I have a system that conserves not just charge, but also a dipole moment. So you have sort of a higher multipole moment. And there the interplay with translation symmetry is a little different. And I'll talk about that and how this argument generalizes. So the first thing I want to talk about is, what kind of systems conserve dipole moment? So here's our cartoon of electrons in a crystal. And our usual cartoon of electrons in a crystal is that an electron could move, right? It can hop from one site to another, right? And this obviously conserves charge. The electron is not going anywhere. It's still in the crystal. It's just moving over. But this kind of hopping does not conserve dipole moment, right? Because the dipole moment is given by the sum of the, charges times their positions. And so obviously when I change one of the RJs with, and only one of them, this quantity is not conserved. Okay. So when we talk about systems with a conserved dipole moment, what we're talking about is situations where the particles are not free to hop individually, but instead they have to undergo some kind of correlated hopping process. So an example of this, again, in our 1D cartoon is, well, if I just move this electron over, that doesn't conserve the dipole moment, okay? But if at the same time that I move this guy left, I move this guy right, then, oopsie-daisy, sorry. Then you can check that this actually conserves not only the charge, obviously, because these are hopping processes, but it also conserves this dipole moment, right? Because one of them moved to the left and one of them moved to the right. Okay. And it's worth noting that although dipole moment is not conserved when we talk about electrons in crystals, there are a number of physical systems, particularly in one dimension, where dipole conservation is very much part of the, part of the fundamental physics. So the first context that, certainly where I heard this discussed at length was if you take a system and so I guess I should explain what a Landau level is. But basically, if I take a two-dimensional system and I put it in a very high magnetic field, okay, I get a completely flat energy momentum relation. So the energy doesn't care at all about the momentum and a particular, kind of states. These are called Landau levels. And if you've heard of the the quantum Hall effect, these are kind of the basic building block of how we understand quantum Hall states. And so in the early 2000s, people spent some time thinking about what happens if I take a two-dimensional quantum Hall system and essentially turn it into a one-dimensional system, okay, looking at a thin torus limit. And it turns out that you can make some headway in understanding things about the 2D wave functions in this limit. And one of the things that you see in this limit is that these problems become correlated hopping problems. So there's a dipole moment conservation when you take this particular limit. Now that's a bit academic, but more recently, it was also observed that if I have, if I'm working, for example, with a cold atom gas experiment, okay, where people can make, they use lasers to make a 1D lattice, and they can also quite easily in these experiments put, something that from the point of view of the atoms, right? So here's my 1D lattice. This line here is showing the potential that the atom feels in the trap. And they can quite easily take this one-dimensional lattice and tilt it, which, means the potential looks like this, okay? And, to a very good approximation, meaning out to quite long timescales in these experiments, energy is conserved. And so that means that with this background tilt, my atom can't by itself hop up, because to hop up, it would have to gain energy. And similarly, obviously, at some point it's going to interact with the environment, and it's not a completely isolated system. It's not going to conserve energy forever, but let's say sort of up to long timescales, this is true. And it also can't hop down, right? Because to hop down, it has to lose energy. And again, if it's totally decoupled from the environment, it doesn't have anywhere to dump that energy. But what it can do is undergo these correlated hopping processes, right? Where one atom goes up and one atom goes down. Okay. And so, this idea was sort of discussed about 5-6 years ago in theory, and a number of experiments, have been done on these systems. Okay. So, and it turns out that they're pretty well modeled by things that do conserve dipole moment. Okay. So it's not a completely academic argument to talk about it. Good. So when we go from a charge conservation symmetry to the dipole symmetry, okay, you shouldn't be surprised to hear that the interplay with translation is very, very different. And there's some details there that are a little bit important for what I'm going to tell you. So the first thing about dipole symmetry is, of course, if I took my one-dimensional system and made it into an infinitely long line like this, right, I could talk about a continuous dipole charge and continuous dipole symmetry. But we have been talking about one-dimensional systems that live on a finite-sized ring, okay? And if you think about it, on this finite-sized ring, it doesn't quite make sense to say that the dipole charge is totally conserved. And the reason for that is here I have, one particle, okay? And if this particle goes around the ring, right, basically it has changed its position by L, by the size of my system, okay? And, in periodic boundary conditions, right, this is it's now back in exactly the same place. This is a completely physically equivalent configuration. And so that means that, and, again, I'm being a bit cavalier with units here, okay? But if I shift the dipole moment by something on the order of the lattice constant, right? Maybe we should call this L over A or EL over A, right? So that the dipole filling changes by an integer, this is actually equivalent, okay? And so, so dipole filling is something that we should really only talk about modulo integers. Okay. Now, that has consequences for the nature of the symmetry, right? So remember that the symmetry operation, it's exactly as in the charge conservation case, right? I do my symmetry transformation by taking e to the I alpha times this charge and acting on the wave function, okay? Here, the dipole charge is, of course, this dipole moment. But now we know that this dipole moment is really only defined modulo L, okay? And so that tells us that actually, once we impose periodic boundary conditions like this, I work on my finite one-dimensional ring, the dipole symmetry is not a continuous phase rotation symmetry, but rather it's discrete in multiples of 2 pi over L. And again, here I've set the lattice constant to 1. Okay.
So this gives like a ZL symmetry, right?
Exactly. Yeah, that's right. So at a minimum, it's a ZL symmetry. And of course, you can talk about dipole symmetries that are ZP, where P is, some divisor of N. But you can't really, it's not correct to treat it as a continuous symmetry. It's really a discrete thing.
So the boundary conditions sort of compactify the parameters.
Yeah, that's right. So if you, and like if you're like a high energy person, right, they often like to talk about, oh, I just have like an infinite line, right? And if you work on the infinite line, you can talk about continuous dipole symmetry. So that's a thing that you can talk about. If you want to have translation, right, either your line really has to be infinite, but then we can't really talk about this flux insertion, or, you know, you make it finite and you have periodic boundary conditions. So that's the choice that we're making. But that does modify the nature of the symmetry. Good. Okay. Here the particle goes again. Okay. Good. Okay. Good. Now, so that's the nature of the symmetry. Basically, dipole symmetry is discrete. Now, so there's a first observation to be made, right? Which is that we already knew that if we had, because we do have charge conservation symmetry, and the charge is out, you know, the charge is conserved. Okay, there's no conserved modulo L, the charge is just conserved. Okay. And we know that, you know, if we have a fractional charge filling, we already know that, you know, this flux insertion process changes the many-body momentum of our ground state. Okay. But there's a kind of a tweak to that when we have this dipole symmetry, which is that actually the operator that carries out this large gauge transformation that we were using to make our flux insertion argument when we were just talking about charge, this is actually exactly the dipole, right? This is QD right here, and this is a 2 pi, and now I've put back in the lattice constant, okay? But this is our 2 pi over L. This is one of our allowed phase rotations for our dipole symmetry. And so that means that this is an operator that commutes with the Hamiltonian, and so this state psi prime has to have exactly the same energy as the state psi, okay? And so that means that if we work with a fractional charge here, right, so that this these states have different many-body momentum, there's an exact degeneracy, and typically you expect that to mean that translation invariance is just broken, which is certainly what happens in the thin torus limit of fractional quantum Hall systems. Okay, so that's an observation, but for today, I think, you know, maybe for me, the more interesting question is, well, let's suppose that based on charge filling alone, there's no obstruction to having a completely boring ground state, right? So I'm going to have a charge filling fraction that's an integer, 0, 1, whatever. Okay. And now we want to ask, suppose that I add dipole symmetry on top of that, right? So if I didn't know about dipole symmetry, you know, maybe I'm a numericist or an experimentalist and I expect some very boring ground state in this regime. Can it be the case that in the presence of dipole symmetry, I might be forced to not have a boring ground state, right? So that's what we'd like to ask. Now, a priori, when you look at this, okay, you'd be like, well, let's talk about the same flux insertion argument, but now, you know, I can't send a charge around the system, right? I have to, because the charge can't move individually, I have to send a dipole around the system, right? So here's our negative charge and here's our positive charge, right? And they're going to hop around the system, right? And you might say, well, you know, I have the negative charge and the positive charge, and they are actually going to make opposite contributions to the Aharonov-Bohm phase of the wave function, so this is trivial. Now, if you kind of write this out more carefully, what you can see that what you mean by that statement is that the total Aharonov-Bohm phase, and here, you know, this D, you should think of it as a lattice derivative, right? It's like, you know, thing at R plus A minus thing at R, okay? What you really mean by that is that the total Aharonov-Bohm phase is like, you know, the integral of this quantity of the derivative of A around our system. And usually, right, when we're talking about electromagnetic fields, you know, we want our derivative to be single valued, so we would require this to vanish. However, when we're talking about a dipole symmetry, you know, this is not something that you can do, you know, I think with a, you know, I don't know how to get an experimentalist to do this, but the reasonable thing to do to repeat this argument is to do a thought experiment in which you basically allow this not to vanish, right? And the reason is that this dxax, right, if I had some gauge field that coupled to dipoles, right, I wouldn't write this as dxax. I would just call this, you know, a twiddle x, okay? And it has a, you know, it has gauge transformations like dxax, but then I could allow this guy, I could talk about flux insertion and gauge transformations of that gauge field. Okay, so that's sort of the game that we're going to play. Oh dear, I need to stop going back in the slides. Okay, good. So, all right. Okay, so that's the first thing, is that you can and should, if you want to talk about flux insertion arguments for dipoles, kind of extend your notion and say, I don't just have a U1 gauge field, but I have a gauge field that sort of intrinsically couples to the dipole moment. And I can talk, at least as a theorist, I can talk about what would happen if I inserted a flux of that gauge field. Now, the second thing that's a little bit different here is that we just said that dipole symmetry is fundamentally discrete. Okay. And one of the things that I told you when we talked about this flux insertion argument was basically that because I can insert the flux super, super slowly, right, adiabatically, because the flux is totally continuous, right, I can guarantee you that at no point am I like dumping a bunch of energy into my system, so that if I have, a gap between the ground state and the excited states, I can always choose to insert the flux slowly enough that I can guarantee you that I remain in the ground state. Okay. For discrete symmetries, we don't have that luxury because we can only insert the flux in discrete kind of multiples. So the other thing that I'm going to use is that you don't actually need, so the flux insertion picture is very physical and very intuitive, but there's a different way to think about these flux insertion arguments. Okay, so we don't actually need to talk about it quite as like adiabatically inserting flux. And the other way to talk about this, and this was a result that was shown in a paper by Gaoya and Wang, okay, the other way to talk about this is that if you have an operator, which is just a product of local operators, okay? So here our large gauge transformation, right? This is obviously a product of operators where each operator is just, e to the I 2 pi over Lx times j and j. So I have a product of an operator on each side, okay? And what they showed in this paper is that if I take a product of local operators, such as our large gauge transformation, and this changes the many-body momentum, then your ground state cannot be boring. And specifically, boring means that it's adiabatically connected, or what they showed more precisely was connected. This is a picture of a quantum circuit, okay? And what this is supposed to show is that I start with a product state. In this case, it's a spin system. Everybody is spin up, so all zeros, okay? And then you apply a sort of short unitary circuit, okay? You should think of this as, roughly speaking, like doing your adiabatic evolution, and I get a state like this, okay? And basically what they showed is that if there's, if I can just add some layer to this, or a few layers to this unitary circuit that changes the many-body momentum, then I can't have a circuit that connects this to a product state, okay? And that's one definition of saying our ground state is not boring. So there's a version of this argument in which we don't need to talk about the energetics involved in flux insertion, and that's the one that you should use when you're talking about discrete symmetries. Okay, and so now, because I'm running short on time,
Can
so
I ask
maybe
something?
Yeah.
Can we determine the degeneracy, like the number of ground states in this argument? Can we count them?
Just from knowing that just from knowing that you have a local operator that changes the many-body momentum, I don't believe that allows you to say how many ground states there are. Although, kind of naively, right, you can apply this operator some number of times and you would generate a bunch of different momenta, right? And so I think like, yeah, let me put it this way. I think in this paper they don't talk about that, but intuitively you would expect that if the ground state is gapped, right, that that would give you the ground state degeneracy. But I guess I'm not sure that that's been addressed rigorously. It's a good question. Certainly, if I have fractional charge filling with the dipole symmetry, this is an exact thing, right? You have this exact degeneracy, and the dipole operator tells you can generate the following different momenta, and that gives you the ground state degeneracy. But I'm not sure, kind of in this more general case, if it does. Okay, good. So maybe in the last couple of minutes, I will just sketch. So, as I said, there's a version of this argument where we don't need to worry about energetics, and where we have a large gauge transformation. This is our product of local operators, okay? And it's the analog of a large gauge transformation for our dipole system, okay? And you can again show that this product of local operators sometimes will change the total momentum of our system, okay? It's exactly the same argument. When does that happen? Okay, well, there's a criterion that depends on both the dipole filling fraction and the charge filling fraction, okay? And basically the criterion for this to not change the many-body momentum, so to allow a boring ground state, is that this particular combination of charge and dipole filling fractions is an even integer, okay? And, just to say, this checks out with your naive intuition. Okay, so here I have Q charges on each site. This looks pretty much like a boring state because I have the same number of charges on each site. You can compute the dipole moment for this configuration. It looks like this, okay? And you can now ask, what is this quantity, right, in this case? And you find, so, there's some subtleties because I now care, if the charge is odd, I care whether this L+1 is even or odd. But you can check that, these kinds of states always satisfy our criterion of being boring, okay? However, you can also check, maybe I'll go back here, okay, that it is possible, so there are configurations, not ones like this, okay, but I could have a situation, right, where this is a half integer, right, and this is some, this is some integer. So this is odd, right, and this is even, okay. And our criterion then, so there are situations where even at integer charge filling, right, this is an integer, the dipole filling could give me an obstruction to having a boring ground state, okay. And so maybe that's kind of the moral, and then you can test this numerically. So here's a plot of a Hamiltonian that has dipole conservation. Okay, in this case, it's spin and not charge, and this is in the, total spin zero sector, so spin filling zero, okay? And you can see that as you tune the dipole filling, if the dipole filling is zero, which is equivalent to 1, you have a nice big charge gap, and in between, this system looks very much gapless, okay? Okay. Yeah, so that's basically what I wanted to say. Just to recap, I think that these Lieb-Schultz-Mattis type arguments, these kinds of arguments that basically ask, suppose I have the following symmetries and the following fillings, is my system forced to do something a little bit interesting? I think they're very simple and also very useful for characterizing materials. And I told you a little bit about, an extension of these, very basic and foundational ideas to systems with dipole conservation. Okay, and then I'm happy to stick around for more questions.
Thanks for the nice talk. Yeah, is any questions from the audience?
Sure.
I have one question, actually.
Yeah.
So, I'm not sure I get it correctly, but you said that essentially the dipole symmetry is related to large gauge transformations. And if we consider like a gauge theory, large gauge transformations are essentially related to one-form symmetries. But then this dipole symmetry is on a 1D lattice, so we can't exactly talk about one-form symmetry. So how, I was not able to understand exactly how they're related, like large gauge transformations and dipole symmetries.
Oh, okay. So Okay. So basically, yeah, so large gauge transformations, yeah, indeed, sort of at some level, it's the you have this thing, and the thing that's charged under them is, again, a Wilson operator. But I don't think, I mean, you don't need that perspective to talk about them. And I guess the point that I was trying to make is, anytime you have a dipole, right, basically it couples to gradients of whatever the charge couples to, okay? So naively, you would say, well, look, there's no flux insertion for a dipole because I'm going to require the gradient of the electromagnetic field to be single valued. But if you want to talk about dipole symmetry, so there's actually the word that is usually used in context with these is you have like higher rank gauge fields. Okay, so this is something that, so basically, actually, maybe I can maybe I can just write a little bit on the whiteboard. But yeah, so basically, I can call this field, I called it A twiddle X, but we would usually call it like AXX, right? And under gauge transformations, the property of AXX is that instead of transforming like, the X alpha, it transforms with two derivatives of alpha, okay? But if I really want to talk about things that are like gauge symmetries for dipoles, what I should do is I should just allow, I should allow myself to have, I should allow this guy to have winding, okay? And so this dx squared alpha, basically, on the lattice level, it basically, I have like alpha j minus 1, right? Alpha j plus 1. And this tells, this is like, it's like alpha j plus 1 plus alpha j minus 1 minus 2 alpha j. Okay, this is sort of, what the gauge transformation looks like. Okay. And then you can show that the operator, and now you can, calculate some winding of this guy, and you can show that there's a large gauge transformation, meaning like, so now I compute the integral of AXX dl, right? And I can change that by 2 pi by carrying out the gauge transformation where I take like alpha j is 2 pi over L, and then, this one that I wrote down in the talk. So basically I need this quadratic thing. And this shift of the dipole thing is mostly for convenience. But the essential thing is that you can do this large gauge transformation once you have this j squared term. Does that answer your question?
Yeah, a little bit. Yeah.
A little bit. Okay.
I mean, I'm not very familiar with this language, so I'm more used to continuum.
Yeah, but I think, so in the continuum, this would basically say I need some, right? So that the standard large gauge transformation, right, is something like 2 pi x over L, right? And then, A goes to A plus 2 pi over L, right? And then this changes the winding of A around this curve in the x direction by 2 pi. And so we could write down a continuum analog of this, right? Where here we would have like, here we would have, let me erase this. Here we would have alpha is 2 pi. And like I said, the fundamental term is the quadratic term, right? So it'd be something like, 2 pi x squared over L, right? Something like this. And now we take two derivatives of this, and basically, AXX goes to AXX plus 2 pi over L, right?
Okay, I see.
And so that's the basic thing. And usually, yeah, there's some, I'm being cavalier with kind of where the dimensions go, because, usually, because the rank 2 gauge field has a different dimension.
Yeah, but this helps. Thanks.
Yeah.
Okay, so maybe I can stop the recording.